Lesson 11.6 is on ANOVA testing, and ANOVA stands for Analysis of Variance. ANOVA testing is a really powerful testing tool that we have, and you'll see it a ton in various research articles when you look at their results. ANOVA testing is very commonly used. So, ANOVA testing is used when we want to compare the means of 3 or more populations. So that's a key there. Means of 3 or more populations. Everything we've done so far in chapter 11 has been comparing 2 populations. So now we can add 3, 4, 5, or 6, or however many we want. Now, in this class, we're only talking about one variable ANOVA, but we can expand this process to do multivariables. That is beyond this course, but just so you know, it does exist. So when we perform ANOVA testing, the null hypothesis states that all the means are equal. So mu1 equals mu2 equals mu3, however many you have. And the alternative hypothesis is at least one mean differs from the others. This alternative hypothesis is always stated exactly like this, okay? The only change in the null hypothesis is the number of mu's you have. But the alternative hypothesis is we always say that at least one mean differs from the other. Now, when we're doing this, we know that sample means are not going to necessarily be equal. So we are testing to see if the variation is due to chance or a true difference in population means. So for example, if we wanted to look at like average ACT scores for different races, so maybe mu1 is for Caucasian and mu2 is African American, and mu3 is Asian, and mu4 is Native American. So our null hypothesis that everyone has the same average ACT math score, and the alternative is at least as one is different. Now, when we pull sample data, we know that there's going to be some variation in it just because of the sample that we may have chosen. So we want to know, is that due to chance or is there actually some difference? That's what ANOVA is testing. So in order to use ANOVA, we need simple random samples. They have to be independent. All the population variances are nearly equal, and population distributions are approximately normal. We do not do ANOVA testing by hand. That would be a disaster. There's a bunch of terms that you need to know. I'm just going to go through these really quickly. They can be found in your book when you read the section. I've referenced the page numbers. A lot of these formulas are on your yellow reference sheet as well. So the grand mean is the weighted mean of all of the sample means. Sum squares among treatments, that's SST. It measures the variation between the sample means and the grand mean. So think of it like a standard deviation, sort of. Sum of squares for error measures the variation in the sample data resulting from the variability within each sample. So think of that as a standard deviation within each sample size. Total variation is we take the SST plus the SSE. So that's what we use for that. Mean squares for treatments is SST divided by DFT. That's the degrees of freedom of the treatment, which is K minus 1. K is the number of samples. Mean square for error is MSE, and we find that by taking SSE divided by DFE. That's the degree of freedom for error. And finally, the test statistic, it's going to be an F value. You take MST over MSE. You don't need to know all of those things. A lot of them are on your yellow formula sheet. We just need to be able to read and understand an ANOVA table, which is what we're getting to next. So the larger the difference between each pair of population means, the larger our F value is going to be. So a large F statistic supports that one of the population means is different. Generally, you're also going to have a p-value, so we don't really need to use rejection regions. So let's take a look at this first example. And it has a ANOVA table, so I'll show you that. So medical researchers studying the effect of vitamin C on the common cold group study participants into three groups. So group 1 took a lot of vitamin C, group 2 took some vitamin C, and group 3 took no vitamin C. And then we observe them for a year and we count the number of colds, and we want to record the mean number of colds. So I want to go ahead and write the null and alternative hypothesis just so that we have that to reference as we're talking about this. So what we're saying is our null hypothesis is the people that got a lot of vitamin C and the people that got some vitamin C and the people that got no vitamin C, their mean number of colds were all the same. And then our alternative hypothesis is that at least one mean differs. All right, so the first thing we need to do is fill out this table. So we have our SS, which is our sum of squares, treatments and errors. And then right here, you see we have total. So that means this number plus this number has to give you that 52.0606. So to get that number, let me erase that so we can actually see what's going on here. So to get this number, we're going to take 52.0606 minus 49.2030. And when we do that, we get 2.8576. That's what goes in that box. I can't fit it in there, so I'm not going to put it. Degrees of freedom, again, you've got the total right here. So degrees of freedom of treatment is 2. That means degrees of freedom for error has to be 30. Oh dear. Because they have to add up to 32. All right, for this one, now there's no total column, so this is a little different. This is MSE, and remember, that's a mean squares. Now on your formula sheet or in your book, MSE is equal to SSE over DFE. That is on your yellow formula sheet. So let's see. SSE is somewhere. Oh, it's right here. 49.2030. Degrees of freedom of E is this number right here that we just found, 30. So when you divide those two things, you get 1.6401. And then the last thing that we were supposed to calculate is this F value, again on your yellow formula sheet. F is MST divided by MSE. MST is this number right here, 1.4288. And MSE is what we just calculated here, 1.6401. And when we divide that, we get 0.8712. I apologize for the messiness on this, but hopefully you can see what's going on. All right, let's change color here so we can see something. Ignore that. All right, so do the researchers have enough evidence at the 0.05 level of significance to support the claim there's a significant difference between the mean number of colds? All right, so there is an F critical value, which we don't really care about. What we want is the P value right here. We know that P is 0.4288, and we want to compare that to our alpha level. Clearly, P is much larger than alpha, so we are going to fail to reject. So we're going to fail to reject H, our null hypothesis, which means we have to accept this. So we would say there's not sufficient evidence to support the claim. And can we conclude if one group has fewer colds than the other? No, we can't. Okay. So there's not sufficient data to say that the mean number of colds differ from these groups. So that's what an ANOVA table looks like. Generally, you're going to have that all spit out for you, but that's how you fill it in if you don't. Now, your calculator runs an entire ANOVA test for you. Okay. You have to put all of your data into L1, L2, L3. It depends on how many you have. You can do L4 and L5. You go to stat, test, and then ANOVA, and you just have to tell it where all your data is. ANOVA testing is the very last thing. It just has parentheses. So you have to do L1, comma, L2. Remember, the comma button is directly above the 7. You have a button for comma. So let's see, this is our only other problem for today. This is it. All right. So researchers at a drug company wish to test whether their drug is best on the market for lowering cholesterol in middle-aged women. So they've got 30 women with high cholesterol who volunteer to take part in this study. They're divided into 3 groups. They're each given a different cholesterol-lowering drug, one of which is made by this company. And then they measure the cholesterol levels at the beginning and again after 6 months, and the difference is recorded. This is on page 771. So you're going to actually have to pull your book out because I didn't write all these down because it was a lot of numbers. So, but let me get you what we need as far as our null and alternative and all that. So our first step is we are going to write our null hypothesis. We have 3 different groups, so we're going to say that mu1 is equal to mu2 is equal to mu3. And our alternative hypothesis is that at least one mean differs. Handwriting is not going well right now. All right, we are doing an ANOVA test at 0.10. And now you're going to put this data into your calculator to see what it can do. So you're going to go into L1 and you're going to list all of the data for drug number 1. And then in L2, you're going to list the data for drug number 2. And then L3, you're going to list all the data. And again, this is on page 771. So go ahead and put that in your calculator. You may need to pause the video to do that. Once it's in your calculator, you're going to go to Stat, Test, and ANOVA. It should be the very last thing. You're going to do ANOVA L1, comma L2, comma L3. And the only thing that we really care about once you put all that data in is the p-value. So your calculator should come back with p equals 0.0744. We're going to compare that to alpha, and it is smaller than alpha, so our decision is to reject the null hypothesis. So we're saying not all of these means are the same. So the way we interpret this is we're going to say at the 0.01 level of significance, I'm going to abbreviate that, the data supports that at least one drug, or at least one group, had a different mean cholesterol decrease. Now, one thing I want to make note of about this, we do not know which one. We cannot say which group differed. Not from this test, okay? So we could go back and look at the data and say, maybe I think it was drug number 2. But if you wanted to compare drug number 2 and say, I think drug number 2, decreased cholesterol more than drug 3, then you would have to go back and do a test of just 2 and compare them. So that way you could do a left or a right tailed test. This does not tell you which one. So you would have to go back and say, well, it looks like it's this one, and then run additional test. So be super careful with that. All of this ANOVA testing is that one mean differs for this. So that's ANOVA testing. I strongly encourage you to read that section of the textbook so that you can see it with a lot better handwriting than what I just gave you. But the calculator really does a great job with these.